All right, so this is the second part of chapter 3 lecture. So here I'm going to talk about the projectile motion. Okay, so what is the projectile motion? Projectile motion is one of the simple illustration of motion in 2 dimensions. So although it says simple, but if you do not understand the how two vector can be added, or if you do not understand the kinematic equation in chapter 2, then it is not that simple. Okay, so although it says the simple illustration, it's not that simple. Okay, so the first thing you have to understand is kinematic equations, and then how to add 2 vectors, okay, or how to resolve a vector. Okay, so they're connected. So once you know that, once you have this background, then the rest of the things are not that difficult. Okay, and similar to the free fall problem, here we are also going to neglect the air resistance. Okay, so once you neglect the air resistance, then projectile motion is only due to the influence of gravity. Okay, so if you do not neglect the air resistance, the things will be a little bit complicated, and we are not going to learn the complicated thing in this course, in the General Physics 1 course. Okay, so for simplicity, we will be neglecting the air resistance, very similar to free fall problem. Okay, now the projected object we normally refer to as projectile. Okay, so here I show some real life example of projectile motion, and you see that the projectile motion here, for example, these marbles. Okay, so here you see the marbles motion is projectile motion, and marble here is the projectile. The basketball here is the projectile, projectile, and its motion is projectile motion. Here is the water is projectile, and water motion is projectile motion, and so on. Okay, and you see that for all the real life problems, the motion is parabolic. So you see that mathematics, if you remember from the geometry, so this is a parabolic path. Okay, this is a parabolic path. So the projectile motion follows a parabolic path. Okay, all right. So let's say we project some object, okay, at some initial velocity v0. So this is our coordinate system. So this is let me use another color, red probably. Okay, so let's say this is coordinate y and this is coordinate x, and we have a projectile here. Let me think, let me say that it is a soccer ball. Okay, so let's say we have a soccer ball somewhere here, and we project it. Here projecting means kicking. Let's say we kick a soccer ball with some initial velocity v0 that makes an angle theta with the horizontal or the x-axis. Okay, so what we have here is we project something here, a soccer ball, for example, with some initial velocity v0, and this v0 makes an angle theta with the positive x-axis. Okay, now you know that v0 is a vector, right? Velocity is a vector. So because this vector makes an angle theta with the horizontal or the x-axis, we can resolve this vector. We can break v0 into its components, right? And as you learn that v0x, okay, so the x component of v0 will be, so this is adjacent, right? Adjacent is cosine theta, so it will be v0 cosine theta. So this is v0 cosine theta, v0x, and this is v0y, and v0y is equal to v0 sine theta, right? Sine theta because it is opposite. You can basically say that this is v0y. Okay, so this and this parallel and same length. So either this is v0y or this is v0y. Okay, so the first thing we have to understand that when you project an object at some initial velocity that makes an angle with the horizontal, okay, then we can break this vector into its component. So the component vectors are, vector components are this and this. So this along the x-axis, this along the y-axis. Okay, so once we have that, the next thing we have to understand is if we neglect the air resistance, and for simplicity, we are going to neglect the air resistance in this chapter for the projectile motion problems. Okay, so once we neglect the air resistance, the only thing that affect the motion of the object after you project, after you kick the soccer ball, is the gravity. Okay, so after this point, after the origin, okay, after you kick, after a cannonball is fired, okay, so after it fired, after you kicked, the only thing that affect the motion of a projectile, okay, is gravity. Okay, and as you know that gravity is always downward. Okay, gravity is always downward. Okay, so there is no component along the x-axis for gravity. So we'll have gravity because gravity is the only thing that can affect the motion of the object, and that is along the y direction, right? So we have gravity, and we have, that means we have a gravitational acceleration only along the x-axis, only along the vertical direction. So we'll have gravity along this direction, not along this direction. And because the only thing that can affect the motion is gravity, we cannot have acceleration along the x-axis. So acceleration along the x-axis will be 0. So if you understand this thing, then the rest of the thing are very simple. Okay, so let me say again, let me talk this thing again, let me repeat it. Okay, so this is the ball, soccer ball or cannonball, whatever. Okay, so let's say we project it. So in general, we can say that we project it. So we project it at some initial velocity. So this is the initial velocity. Okay, so v0. And let's say this makes an angle theta with the horizontal. So if a vector makes an angle theta with the horizontal, then we can break it into components. So this is the x component. Okay, so x component is cosine theta because cosine theta is related to the adjacent, and this is the sine theta. It is the v0y, the y component, and y component is because it is opposite to the theta, so we should have the sine function here, v0 sine theta. Okay, so this is y component and this is x component. After that, you have to understand that just after we project it, the only thing that can affect our motion, that can affect the object's motion, is just the gravity if we neglect the air resistance. Okay, so here, because we neglect the air resistance, only thing affecting the motion of the object is the gravity. And gravity is associated with the gravitational acceleration, and gravitational acceleration is only along the y direction, vertical direction. Okay, so because gravity is along the vertical direction, we can have only acceleration along the vertical direction. Okay, there will be no acceleration along the x-axis. Okay, so ax will be 0. Okay, so x will be equal to 0. Now what it means? It means the motion of the object is combination of two things, two separate things. Okay, so one thing is, so let me erase all those things, okay, and summarize here. Okay, so it is the combination of two things. The one thing is object is moving in this direction with initial velocity v0x or v0 cosine theta. So an object moving in this direction with this initial velocity, and zero acceleration, okay, plus an object is moving in this direction with this initial velocity, okay, and acceleration equal to gravitational acceleration. So when we combine this and this, we basically get this motion, okay. All right, so we'll now use the kinematic equations to understand the mathematics, okay. The first thing we have to understand is a projectile motion is combination of two motions. One is this, one is this, okay. So there is no acceleration along the x-axis. There is acceleration only along the y-axis, and that is the gravitational acceleration once you neglect the air resistance, okay. All right, so the next step is to understand. So here I already summarized, so if you don't understand, please read it again and try to understand what I tried to say here, okay. Now we need to write two set of equation, one for the x-axis or horizontal motion and another for the vertical motion or y-axis, okay. Remember that for x-axis there is no acceleration, for y-axis there is acceleration, and that is equal to the gravitational acceleration, okay. Basically we need these four equations, okay. Two of the kinematic equations, okay. So remember that we had kinematic equation. So let me write down the kinematic equation here and then choose from the list. Okay, so the first equation was x equal to x0 plus v var t. Second one is v equal to, so this is v equal to v0 plus at. The third one is x equal to x0 plus v0 t plus half a t square, and the fourth one is v square equal to v0 square plus 2a x minus x0, okay. Now for the we basically need these two equations, okay. We have to modify these two equations twice, okay, one for horizontal direction and another for vertical direction, okay. So let's take v and x equation for horizontal motion, okay. So horizontal means x, so let me use subscript x for this, okay. So the first equation can be written as this vx, so you see that vx v0x axt, okay, and then x equal to x0 v0xt plus half axt square. So basically we don't need this equation, we don't need this equation, okay. And because we now have both components, so to differentiate x component with y component, I use subscript x. So here you see v is now vx, v0 is now v0x, okay, and then here v0 is now v0x, okay. So as you learn in the last slide that there is no acceleration along the x direction, okay. So this term is zero, right? So this term is zero, this term is zero, okay. Normally x0 is zero because we normally start from the origin. So for example here, okay, so this is the origin. So when you kick the soccer ball, okay, you can choose that this is the 0 0 position, okay. So x0 equal to 0, y0 is also equal to 0. So you can also neglect these x0 and y0 in your equations, okay. So once you neglect all these, so the final equation becomes very simple for the horizontal motion, okay. So you see that the final equation is vx equal to v0x, and v0x is v0 cosine theta, okay, as I already mentioned it, okay. So vx equal to v0x, okay, and x equal to v0 xt, so only remaining term is this one, okay, and v0 x equal to v0 cosine theta, so the equation is something like this, okay. Now this equation tells us that there is no change in the horizontal velocity. So you see that at any later point the velocity will be equal to the initial velocity. So along the horizontal direction, in this direction, there is no change in the velocity, okay. It's always equal to the initial velocity, and that makes sense because there is no acceleration along this direction, so there is no change in the velocity, because you know that acceleration is the rate of change of the velocity. Because the acceleration is equal to 0, the velocity does not change, velocity remains constant, okay. All right, so that's about the horizontal motion, okay. Now about the vertical motion. So for the vertical motion, you see that the same two equation. Now I write Vy, I use subscript y because it's along the y direction, and V0 now is V0y, and A is now gravitational acceleration. The acceleration is now gravitational acceleration, and now I also use a negative sign, as very similar to the free fall problem, because negative sign tells us that the gravity is downward, okay. So that's why I use a negative sign. And the same thing for the second equation. Instead of x, I use y to represent that it is along the y direction or the vertical direction, and v0 I replaced it by v0y, okay, to differentiate it from the v0x. A is replaced by g, the gravitational acceleration again, and a negative sign tells us that the direction of the gravitational acceleration is downward, okay. So these are the two equations for x-axis, and these are the two equations for the y-axis. So once you know these four equations, you are ready to solve any projectile motion problem, okay. But before that, let me discuss few more things and then solve problem. But we are going to solve problem in the next lecture, not in this lecture, okay. So similar to the x equation, now if you substitute the value of v0y, remember that in the last slide we wrote that v0y equal to v0 sine theta, right? So we replace v0y to v0 sine theta, and same thing here, v0y equal to v0 sine theta, okay. Then we have these four equation that can explain all the projectile motion problem, okay. All right. All right. So before I do this, before I talk about the horizontal range and level horizontal range, let me show you a simulation, interesting simulation, okay. All right. All right. So here you see we have a cannon, okay, and we have the option to change it direction. So you see that you can change the angle, and you have also the option to change the initial speed, but we can only do until 30 meters per second, okay. And here we have also option to change the cannonball as different things. So you see that you can use car, piano, human, many things, many options, okay. And you can also change the cannonballs, okay. The mass of the cannonball. Diameter is not that important. You can also change the gravity, but let's keep the gravity as 9.8 or 9.81 meter per second square, because this is our gravity on the surface of Earth, okay. All right, another thing you can do is you can turn on or off the air resistance. and of course we don't want air resistance. Okay, so if there is air resistance, you will see that the motion is little bit different, which we don't want. Okay, all right. All right, so what happens if we fire the cannon? So you see that it follows a parabolic path. Okay, so that we already see from the slide. Okay, so if you change the angle, you will see that it also changes the parabola. Okay, if we change the initial speed, you will see that it also changes the path. Okay, trajectory. So depending on many factor. Okay, so either you can change the parabola or the motion of the object by changing the initial speed. You can change it by changing the angle, right? You can also change it by changing the gravity. Okay, all right. Now the one interesting thing I want to show you is so let me make it 10. Okay, small value. So now I fire it. So it's a cannonball. Okay, so I fire it. So I got here. Now, if I change it, okay, let's say I am using a pumpkin. Okay, so you see the pumpkin hits exactly at the same point. Okay, if I use a piano, you will see that it is hitting at the same point. Okay, so when we have air resistance, okay, I mean when we neglect the air resistance, it is possible. Okay, so when we have air resistance, okay, it may not be the same thing. Okay, so when there is no air resistance, no matter what, how big an object is or how small an object is, always for some initial speed, okay, the trajectory is the same. Okay, although you know that for projecting a piano at 8 meters per second, you have to do a lot of work. But I mean, whatever, if you can project a piano at 8 meters per second initial speed, okay, then it will exactly hit the same point if there is no air. Okay, on the other hand, let's turn on the air, I mean air resistance. You will see that for large object it doesn't matter, but for small object it will be different. Okay, so for example, golf ball. Okay, so let me erase this. So with air resistance, you see that golf ball hits here. Okay, now without air resistance, so you see that it's slightly different. Okay, but it is different. Now if we have a large object, okay, so erase it. For large object, for example piano, you will see that they are not that different. So it's a without air resistance, and this is with air resistance. Oh, so you see that they are different. Okay, slightly different. Okay, so when there is air resistance, it's different. Okay, so if you want to use the air resistance, the equation will be little bit different. Okay, so to avoid this problem, we are always neglecting the air resistance in projectile motion problem. Okay, all right. Now so few things here I want to tell you is okay, so erase this. And all right, so okay, so here I want to tell you a few more things. So when you project something, it follows this parabola. You already know that. And the thing I want to tell you is, you see that this is the maximum height. Okay, similar to free fall problem, this maximum point we call apex. Okay, and at apex or at maximum height, Vy equal to 0. Okay, so Vy equal to 0. That doesn't mean Vx equal to 0. Okay, so Vx is always, no matter where it is, Vx is always equal to V0x or V0 cosine theta. So at each point here, the V0x is, Vx is equal to the initial velocity. Okay, I mean when there is no air resistance. Okay, basically for this. Okay, so at apex or at maximum height, okay, Vy equal to 0, the y velocity equal to 0, similar to the free fall problem. Remember that in free fall problem, at the maximum height or at the apex, the velocity was equal to 0. That time we had only one velocity, but here we have the x component and y component, so you have to be careful. At apex here in the projectile motion, the apex or at the maximum height, the y velocity, the y component of the velocity is equal to 0, but the x component is still equal to the initial velocity. No matter where is the object is, the x velocity is always equal to this. Okay, always equal to v0x. Remember that. Okay, and from this distance, the maximum horizontal distance we call the horizontal range. Okay, horizontal range, okay, or horizontal level range. Okay, so that we are going to derive now. Okay, and then we come back again here to show some other thing. Okay, so let me go to the slide and show show the equations for the horizontal level range, and then few more things. Okay, so here also you can see that the length of the arrow for v1, I mean vx, okay, so v0x, v1x, v2x, so this is basically v2x and v3x, so all are same. So the x, this length are all same. That tells us that v0, I mean vx, no matter where it is, it's always the same. Okay, on the other hand, you can see that the y length of the y component changes. So here, and the direction also changes. So here you see that it is in this direction. You see now its length small. Here at this point it is equal to 0, and here it changes its direction. Okay, and so on. It's very similar to free fall problem. Okay. Okay. The next thing I'm going to tell you is the horizontal level range or horizontal range. Okay, so horizontal level range or horizontal range, we use R for horizontal level range. Okay, and the time of flight, we use a symbol T for the time of flight. So time of flight means the time it takes to go from the initial point to the final point. So the time of flight, I mean the time is in the air, is basically the time of flight. So the time it takes to go from starting position to the end position, that is the time of flight. Okay, all right, so time of flight we use T, and for horizontal range or horizontal level range is R, capital R. Okay, so now as this is the horizontal distance, and we have equation x equal to v0x t, right? So this is one of the equation. So here, so this is the equation, right? This is the equation. So x equal to v0x t. Okay, so or v0 cosine theta t. Okay, now if I replace x by r and t by time of flight, we get this. So this is basically the equation for horizontal level range. But we cannot use this equation here. There are two unknown. One is r, another is capital T. So we have to do something more to make it useful. Okay. So to make it useful, we have to calculate the time of flight from the second vertical equation. So that means we have to calculate time of flight from this equation. Okay, from this equation. This is one of the equation, or the second equation in the vertical direction. Okay. All right, so let's start from this and let's try to calculate t, the time of flight. Okay, so how to calculate the time of flight? So time of flight is t. So here I replace t by t and t square by capital T square. But how I write y equal to 0? Y equal to 0 because y0 is already 0. Now this is y, okay? And this is, because this is y, the final position, final vertical position, and because it is on the ground, so y equal to 0. So the final position here is equal to 0. Now if this is 0, we get this equation. We get this equation, right? Now if I simplify this equation, okay, I get something like this. Okay, I get something like this. Now this equation has two solutions. Okay, one is, okay, let me go to the next slide. One is t equal to 0, equal to 0, but this cannot be the solution because t cannot be 0, right? It travels some time, so 0 cannot be the solution. So other solution is when this part equal to 0. So when v0 sine theta minus half gt equal to 0, we get the time of flight. So when we simplify this equation, so v0 sine theta equal to half gt, and then if I solve this equation for t, I get 2 v0 sine theta over gravitational acceleration. So this is the time of flight. Okay, so once we have the time of flight, okay, then we can substitute this equation, this expression for time of flight, to the horizontal level range, and we get something like this. Okay, so the horizontal level range is this equation. Okay, and then I substitute t. So you see the t equal to 2 v0 sine theta g. We substitute this here. Okay, then do some trigonometric trick. So we use some trigonometric identity. So in the numerator, in the denominator, we still have only the gravitational acceleration. On the other hand, in the numerator, we have 2 v0 square. So v0 square 2 cosine theta sine theta. Okay, so here you see that v0 square and 2 sine theta cosine theta, and 2 sine theta cosine theta in trigonometry it is equal to sine 2 theta. Okay, so the horizontal level range is v0 square, this v0 square, and 2 sine theta cosine theta becomes sine 2 theta. That is equal to the gravitation, and that is divided by the gravitational acceleration. Okay, so r equal to this. All right. Okay, so a little bit of algebra here. Now this is the range, right? R is the range. Now I want to know what is the maximum range. How far we can go if we don't change the v0. Okay, so for example, the gravitational acceleration is a constant, right? For example, if we do this experiment here on the surface of Earth, it's basically 9.80 meter per second square. So we cannot change it. Okay, now we can change v0 or theta. So now my question is, if we don't change V0, okay, so at what angle the range will be maximum? Okay, so of course, if we change the V0, the range will be different. Okay, but I want to know for a particular initial velocity at what angle the velocity will be maximum, sorry, range will be maximum. Okay, so that I want to know. Okay, so we can do mathematically or we can use the simulation. Okay, so first let's try mathematically, and then I'm going to show the simulation whether it makes sense or not. Okay, all right, so this expression is maximum, okay, if you don't change V0. Okay, this expression will be maximum when sine theta 2 is maximum. Okay, and the maximum value of sine function is 1. Okay, so sine, where I mean this R will be maximum when sine 2 theta equal to 1. Okay, that is the maximum value of sine. Now 1 is the value of sine 90 degrees. So if you use your calculator for sine 90 degree, you will find 1. Okay, so sine, I mean the maximum value you get when sine 2 theta is equal to sine 90 degree. Okay, so this tells us that 2 theta equal to 90 degree and theta equal to 45 degree. So this simple calculation tells us that we can reach the maximum range if we project something at 45 degree. Okay, now here I have a simulation. I mean, I draw this from some mathematical software. So you see that if I don't change the initial velocity, okay, so I keep constant the initial velocity, and you see that for 45 degree I reaches the maximum horizontal range. Okay, so here you see that the green one is this one is the 45 degree. So even if you increase the angle, you see that it's below 45 degree. Okay, the range is less than 45 degree. Okay, all right, so you can prove it by using the simulation I already show. Okay, so let me use it again and show you. Okay, so let me keep the initial speed as this, and now it is 80 degrees, so fire it. Okay, now let me change it to 60 degree. So here it is. Let me make it 45 degree. Okay, so 52 degree. Okay, so this is 52 degree, and now 45 degree. Okay, so you see that this is the maximum. So you see that 45 degree, this one is the maximum one. Okay, so and it makes sense, right? And yeah, this tells us that if we don't change the initial speed, okay, the maximum range we get when we project the object at 45 degree angle. Okay, all right, so another thing I want to show you here is this one. So let me erase this. Okay, another thing I want to show you here is this thing. Okay, so 30 degree. So this is 30 degree. Now I change it to 60. Okay, so you see for 30 degree and for 60 degree, the same horizontal range. Okay, and let's say 75 degree or 80 degree. Okay, so 80 degree. So this is 80 degree. Okay, now 80 degree, and then all right, so 80 degree and then 20 degree. So 82, 45, 35, so 10 degree actually. Oh, so that doesn't work. So let me use another 75. Okay, I cannot. Okay, so another one is, so here I don't, I, okay, so 55 degree. Okay, so this one is 55 degree and then 35 degree. So you see that for 55 and 35 is again the same thing. So 60 and 30, 55 and 35 give us the same horizontal range. Okay, so what it means, to understand that, let's get back to the slide. And here you see that we get same horizontal range for two different angle. Okay, and how to calculate this angle? So in trigonometry, there is another identity, and that identity is this one: sine 2 theta is equal to sine 100 degree minus 2 theta. Okay, so now if 2 theta is equal to 60 degree, okay, so theta is equal to 30 degree. Okay, now if 2 theta equal to 60 degree, 180 degree minus 2 theta, so that means 180 minus 60 is 120 degree. Okay, so theta is 60 degree. Okay, okay, so when theta equal to 30 degree, okay, you see by using this equation you can show that another angle will be 60 degree. Okay, and you know that uh, and you already see it in the simulation, right? So using this identity, we can show that for 60 degree and 30 degree, the horizontal range will be the same. And also we can show that 55 degree and 35 degree, the range will be the same, and so on. So here I also show that 75 degree and 15 degree. Okay, so how to remember this trick? I mean, what are the pairs? Either you can use this identity, trigonometric identity, if you understand it. Okay, sine 2 theta equal to sine 180 degree minus theta. Okay, and how they're related? They're related by this equation. Okay, so if you know theta equal to some value, for example, if theta equal to 55 degree, the other theta will be 90 degree minus 55 degree. Okay, and that is 35 degree. So if you know that one theta is equal to 60 degree, other theta will be 30 degree. Okay, if you know that one theta is 75 degree, other theta will be 90 minus 75, and that is equal to 15 degree. So that's how you can know the other theta for which the horizontal range will be the same. Okay, all right. So that's why 30, 60, 55, 55, 35, and then 75, 15 gave the same horizontal range. All right. Few more things. So it's a very special case when the projectile motion from a height launched horizontally. Okay. So uh, what happen if we launch something horizontal? That means we shoot something in this direction. Okay, so when we shoot something in this direction, it follows this path. Okay, again, it is a part of a parabola. Okay, now when we shoot something horizontally from some height, then this time, okay, because this time we are shooting something horizontally only, we will have initial velocity that is equal to v0, the initial velocity. Okay, and vy0 will be 0. Okay, that's because here theta equal to 0 degree. Okay, so as you know that v0y equal to v0 sine theta, right? And sine 0 degree is 0, so v0y equal to 0. On the other hand, cosine v0x equal to v0 cosine theta, and cosine 0 is 1, so v0x equal to v0. Okay, so if you understand this, then all the equations are basically the same thing that you used in the general projectile motion problem. Okay, so only one thing is different here is when you shoot something horizontally from some height, then theta equal to 0. So when theta equal to 0, v0y equal to 0, and v0x equal to v0. Okay, with that, the four equation you needed, you need for this problem are these. Okay, so you see that now Vx equal to V0x, V0. Okay, earlier it was V0 cosine theta, now it is just V0. And here again it was V0 cosine theta times t, but V0 cosine theta is basically V0. So these are the two equations. And similarly, the y equations are again simpler, because now our v0y equal to 0. Okay, so then the equation becomes just vy equal to minus the gravitational acceleration times t, and y equal to minus half gt square, because this is 0 and again this is 0, so the first term becomes 0, so we have basically only the second term for the y equations. Okay, vy equal to minus g times t, and y equal to minus half gt square. All right, so we'll solve this kind of problem, and you will see that solving problem will make the concept more clear. All right, but it's better to first go through the theory and then solve the problem. Okay, all right. The last thing is the relative velocity. Although here I'm going to talk a little bit about the relative velocity, but it will be better to understand the relative velocity when we solve some problem. Okay, so relative velocity, so far we did not much care about the relative velocity. Okay, but let's say if we have a problem something like this, let's say a boat is going from one shore to another shore, one side to another side, but let's say there is now river current. Okay, so if there is no river current, then it is simple, right? If there is no river current, it's just the boat's velocity or boat's speed. Okay, but now if we have a river current, okay, then if you want to know what is the net velocity, what is the resultant velocity of this boat, okay, then we have to consider this river current, right, and also the boat's velocity, okay, and then you have to use the vector addition that you learn at the beginning of this chapter, okay. So if you understand how to add the two vectors, then it's simple, okay. So let's see here what we have. So let me erase this, okay. So we have a river current that is going from east to west, and the boat is going from south to north, okay. So this is river current, okay, and this is boat's velocity with respect to water, okay. Now I want to know what is the boat's velocity with respect to shore, okay. So how to find that? So you see that this is river current, okay. River current means water's velocity with respect to shore, and then this is boat's velocity with respect to water, okay. So then this is one vector, this is another vector. We want to know what is the net velocity or the resultant velocity. It will be the tail to tip, right? So this will be the resultant, okay, tail to tip. And then solving this problem is very easy because this is perpendicular, these two are perpendicular. If you know this and this, then you can determine this by just using the Pythagorean theorem, okay. So we'll see some problem in the problem solving lecture, okay. So here I'm going to stop, and in next lecture I will be talking about actually we are going to solve some problem using the concept that you learn in this lecture and the last lecture. All right.